Okay, good morning, afternoon to everyone. Can you guys hear us? Can someone type? Can you hear us? Okay, thanks, Patrick, Jake. Cool. So welcome to episode probably something like 10 of the Stark at Home series. We're still at home, you know, the virus is still doing its thing. And it's a great pleasure to hand over the mic in 2 minutes over to Professor Swastik Poparty of Rutgers University, who's also a close friend and collaborator for many years. And he's gonna walk us through some nice result that he co-authored. He'll present it. So basically, without further ado, Swastik, please take it over.
Okay, hi. Okay, great. So I'm very happy to give this talk. I'm going to share my screen now. This. Let's see. And okay, so I'm gonna scribble. So the scribble came here. Did it come there? No, you can't see my scribble, it seems, right?
Not yet. In the meantime, I'll remind all those attending, if you forgot, that the way we work is that Swastik is going to talk a little bit from time. If you have any question, you can, push this, ask a question, and from time to time he will, we'll pause and he will answer questions, and then we'll go back. You can also type on the screen. This time, because I'm not going to be scribbling myself, I can answer some questions, on the chat while he's speaking. But basically, I'm going to be here in the role of a producer.
No, not head down. Something not right, right?
Maybe I'll try toggling off your video.
Okay, yeah. Okay, and now I'm writing.
So I don't think, we don't see the screen right now. Maybe when you do share screen, you have to...
Okay, so I'm going to try the whole thing again. So... start the meeting. Okay, good. And now we are sharing that tab. So here it looks. Okay, good. So you can see it now.
Now we see it. All yours.
Okay, great. Okay, good. So I'm going to talk about some kind of distance preservation theorems, which are relevant to low-degree testing, especially things like Fry and Starks, which maybe many of you are familiar with. So let me start off by just setting up I'll just set up the situation we're in, and then you can ask me questions, and then I'll talk about why it's relevant and what we study. Okay, so let me start off by saying that this is joint work with Ellie Ben-Sasson, Dan Carmon, who is also at Starkware, Yuval Ishai at Technion, and Shubhangi Saraf, who's at Rutgers too, just like I am. Good. So the setup is the following. We have, we're in a finite field FQ. There's some subset of FQ, which is of size n. And this is the subset on which we're going to be evaluating functions. Okay, so we're interested in the space of functions f from S to FQ. Okay, the space of all such functions. This is the world in which we live. and this looks like FQ to the n. Okay, and elements of this are naturally represented as strings of length n, each being an element of FQ. Good. And on this, in this world, there's a very natural code which is going to be the star of what we talk about, which is called the Reed-Solomon code. So I'm going to define that quickly. I'm guessing that most of you have already seen what this is. Anyway, so let me know by typing if you want me to elaborate on things. Okay, so the Reed-Solomon code for this setting over the field FQ, the evaluation domain S, and degree, let's go with D. The Reed-Solomon code like this is the space of all functions from S to FQ such that F is the evaluation of a degree D polynomial. Okay, and if D is, and the setting which we like to work with is usually D is less than N. So that's where things become interesting. And let me move that up. D is less than N, and D being much less than N is when really interesting things happen. So for this talk, think of something like D being 0.1 N. That's a really good setting to think about. Okay, so think about. Okay, good. Now, this collection, the Reed-Solomon code of degree D polynomials evaluated at S over FQ, this is a really nice set. Well, first of all, it's a very natural algebraic object. But more than that, its usefulness for the kinds of things that I'll talk about is that it's an error-correcting code. Okay, so let me write down the main property of this Reed-Solomon code that makes it so useful. Good. So for any, so I'm writing here RS of FQ SD is an error-correcting code. And what that means for us is that, so if you take any two elements of this Reed-Solomon code, if you take F and G, which are both in this RS code. So for now, I'll just write RS without the parameters, if you know what I mean. The number of coordinates where F equals G is extremely small. So the set of all X in S such that F of X equals G of X. This is the number of coordinates where F and G agree. This is at most, well, where the equal is at most D, because so provided F and G F is not equal to, if they're not exactly identical, then any two polynomials agree in at most D coordinates. Why? This is because polynomials of degree D can have at most D roots. So the polynomial F minus G, which is a non-zero polynomial, has at most D roots, and so there are at most D points of agreement. Good. So this is the important property for us. Good. So what I'm going to talk about is theorems about when a function is close or far to this Reed-Solomon code. And questions like this are very important for things like Fry, which shows up in things like Stark and other Stark, Aurora, Ligero, maybe. So there are lots of other zero knowledge protocols, etc., of late in the crypto community that build off of this. But I mean, anyway, Reed-Solomon codes are extremely important. But the kinds of things I'll talk about are more relevant to some of the more recent things. Okay, so good. So what my plan now is to state. So I'm going to talk about a specific situation, and then I'll talk about how it connects to the Reed-Solomon testing problem, which is what Fry solves. So, and I'll give a quick overview of Fry, and we'll talk about yeah, we'll see what we want to talk about. If there's the audience interest, then I can give a proof of something small, and yeah, or I can just talk about high-level intuitions and things like that. Okay, so the basic question we'll look at now is: someone writes down a table of values and claims this is an element of the Reed-Solomon code. Okay, so given access to some f from S to FQ, want to check the claim, F is in this Reed-Solomon code. Okay, the question is, how do we do this? Okay, so the table of values has been written down. You can go and poke at any value and find out, oh, what's f of this point, f of this point. You can check whatever you want. You want to check, is f in the Reed-Solomon code? So it turns out that this problem, exactly as I stated, without any extra help, is extremely difficult. You can, or rather, it's impossible. You cannot do it without checking f in many locations. In order to do the task that I just said, you need to check f in at least d locations before you can make any comment on the claim that f is in the Reed-Solomon code. Okay, why? Well, so the basic fact is polynomials of degree d can be used to interpolate any d values. Okay, so there's some d+1 there maybe. So through any 2 points, there's a line. Okay, so whichever sequence of values, whichever evaluations of f that you ask to see, there is a polynomial of degree d consistent with that. So you are at no stage can you have the confidence that what you have seen is inconsistent with the Reed-Solomon code word. So that's why you need to make many queries. So this is the basic question, and the basic answer. So without help, needs d queries. Okay, and in this setting which we're thinking of, d being 0.1n, then this is linear in n number of queries. This is basically as the, I mean, this is within a constant factor of checking the whole table of S itself. So so there's no interesting sublinear time algorithm in this setting. So no sublinear time. Algorithm. Okay, but what we'll talk about now is a different, a way to do it when there is access to some help. Okay, so good. So that's what I'm talking about. Any questions, anyone? Or if a random person is following along, you can say yes. Oh, great. Okay, good. So you need help. Okay, so now the person who made the claim that this function f is in the Reed-Solomon code, we're going to ask that person to say more. That whatever that extra stuff, that we'll ask them extra questions. Oh, you think f is a polynomial? Okay, tell me it's the coefficient of x to the 5. Or you could do things like that. You can ask extra information. If f truly was a polynomial, the person who knows that it's a polynomial could help you out in verifying this. Okay, so we're going to move to protocols of that form. Okay, so good. So now with help, I'm not going to formally define the model. There is a formal model called IOPP, Interactive Oracle Proofs of Proximity. That's the I in Fry. I'm not going to formally define the model, but there's a model where one can formalize what exactly the prover and verifier are allowed to do, and what exactly the soundness guarantee that you want is. And okay, so with help, we're going to talk about a special protocol that does this. So the protocol is the Fry protocol. It's has its origin. So this is by BBHR. This is Eli, Bentov, Horesh, and Ryabzev from a few years ago. It has its origins in a paper from 2005, which was just happened when I joined grad school, by Eli and Madhusudan. And the protocol is really, really nice. So let me spend a few minutes just describing what the protocol is. We have a function which is claimed to be a polynomial, and we want to check that it actually is a polynomial. So, and it's an interactive protocol. The protocol works as follows. So here was this function f from the domain S to fq. What we'll do is we'll take f and break it into two pieces. These two pieces will have the property that they are both defined on their, so f is a vector of length n. These two pieces will be vectors of length n over 2. And we'll reduce the claim that f is in the Reed-Solomon code to the claim that these two pieces are both in Reed-Solomon codes. Reed-Solomon codes of half the length. Okay, so we reduce one claim to a statement about two claims. That f being in the Reed-Solomon code is reduced then to two functions, f0 and f1, both being in appropriate Reed-Solomon codes of half the length. That's what the new claim will be. And then both these claims, f0 and f1 being in this Reed-Solomon code, will be combined into a single claim that a random linear combination of f0 and f1 are in this small Reed-Solomon code. Okay, so let me write that down. So f is this function. We then have a we'll have a subset S prime also inside fq. The size of S prime equals size S over 2. Okay, so that's n over 2 in our notation. So that's n prime. Okay, so we have a subset of half the size. And we have two functions f0 and f1, which are defined on S prime to fq. And we have the statement that f is in Reed-Solomon code of fq s with degree d, if and only if f0 is in Reed-Solomon of fq s prime d prime, where d prime is d over 2, and also f1. So this is and this one and this s prime d prime. Good. So one statement about a vector of length n got reduced to two statements about vectors of size n over 2. This is not a reduction in work yet. But now this second claim will then be roughly reduced to, so this is an approximately equivalent to f0 plus, so I could write it as, so I'll write it as plus z times f1 is in Reed-Solomon of fq s prime d prime for a random z. This is an intuitive statement. It says that, okay, so one direction of this, let me say, is clear. If you have two polynomials of degree d prime, and then you take if you scale one of them, it's still a polynomial of degree d prime. If you add them up, it's still a polynomial, they're still polynomials of degree d prime. So a random linear combination of the form f0 plus z f1, not just random, every linear combination f0 plus z f1 is also in this Reed-Solomon code. If f0 and f1 were truly in the Reed-Solomon code, then so are f0 and plus z. But then so is f0 plus z f1 for every z. This approximate equivalence is that if it was the case that f0 plus z f1, so the other direction is if it was the case that for many z, f0 plus z f1 lies in the Reed-Solomon code fq s prime d prime, then so do f0 and f1. Okay, and it's this that I want to talk about. Okay, so this is yeah. So what was originally proved in BBHR was maybe, let me erase that. So it was originally very squiggly. That's BBHR, and then it over time it got less squiggly. And so what I want to talk about is, okay, so there's still a bit of squiggle. Whoa. Okay, and that's the result that I'm going to talk about today. Yeah. Okay, so I'm going to write an exact statement of that right now. Okay, but the heart of what I'm going to talk about now is the following question. Suppose you have two functions such that a random linear combination of them looks like a polynomial, then the original two functions should also look like polynomials. Okay, so that's the scenario we're thinking about. We have two vectors, we're taking a random linear combination of them, and we're trying to study the closeness to polynomials, the polynomiality of this and the relationship between. So that's the whole setting. Okay, so now's a good time, I think, for questions. So I'm going to write a precise statement of what this connection is, but that's the high-level statement of what I'm going to try to prove or talk about, and what our result is. Any questions?
Do you see the question popping up?
So far, I haven't seen any questions. Okay.
Do you see? At least I can. If you toggle the ask a question, you'll see.
I see a question. I see a question here.
Okay.
What if 0 plus 1 will vanish or be of degree much less than d? Good. Very good. That's a really good question. So, everywhere I cheated. So when I said polynomials of degree d, I meant polynomials of degree at most d. Yes, I meant polynomials of degree at most d. So this space here that I defined as Reed-Solomon codes. Yeah. Okay. Good point. It's degree at most d. Let me circle that in red. Okay, so it's degree at most d. If you say degree exactly d, then that space is a horrible space, because you can't add two elements of it and stay as degree exactly d. Yeah, so you need to put that at most d, and that's what the Reed-Solomon code is. I made a mistake when I wrote this. It should have been less than or equal to d everywhere. And whenever I say degree d polynomial, I mean degree at most d polynomial, except once in a while when I don't mean that. Yeah. Okay. Yeah. Good. Okay, so I'm ready to make a formal statement about the relationship between the f0, f1, f0, the relationship between f0, f1, a random linear combination f0 plus z f1, and the Reed-Solomon code, and distances between all these objects. Okay, I'm going to make that statement now. Okay, I'm making it. Okay, so what we're going to look at is f0 plus z f1 for a random z. So we have f0, f1 are functions from S to fq, and suppose that for many z in fq, f0 plus z f1, the distance, I'm now going to start talking about distances. I hadn't mentioned distances all along. It was sort of in the background everywhere. The distance is the number of coordinates it differs from something. So the distance of f0 plus z f1 from Reed-Solomon codes over FQ of degree D prime. I'll say D prime here. Okay. Oh. Over a set. Oh, this is should have been S prime also. Okay, fine. D prime. Suppose this distance is at most delta. Then the distance between F0 and RS, FQ, S prime, D prime is at most delta, and distance between F1 and RS, FQ, S prime, D prime is at most delta. So this is the theorem statement, but it's a rough theorem statement, and as stated, it's not yet it's not yet true. So where are we? Good. Okay, so this is the kind of statement I want. If you have two functions such that for many z's, f0 plus z f1 ends up being close to the Reed-Solomon code, then individually f0 and f1 are both close to the Reed-Solomon code. You can't ensure that f0 and f1, a random linear combination ends up close to the Reed-Solomon code without making one of them, without making actually both of them close to the Reed-Solomon code. That's what the statement is. Okay, but it's not fully true as stated. I need to say a little bit more. Yeah, so this is for any delta small. Okay, so which is at most. Okay, so then there's some. This works for some radius, only for deltas up to something, and there's some special functions I'm going to write here. So so I'm going to write both. I'm going to write one of them here, and that expression is a Holy expression. There's some Holy number I'm going to write there. Okay. 1 minus square root of 1 minus d over q. And the distance is at most. Oh, sorry. Square root of d over q. So let me write a few things. So this is that's what the condition is. This is called the Johnson radius, or the Johnson-Guruswamy-Sudan radius for Reed-Solomon codes. It's a Holy number. Maybe I'll say more about that later. I need to specify some more things, but okay. Well, the point to note is, so if the distance, I'm sorry, that's not q, that's n. Right. So if the distance is, if the degree d is 0.1 n, as I said, this is the idea. This is an example case to think of. D is much smaller than n, but still linear in n. In that case, d over n is really small. It's a small constant. Square root of that is a small constant. 1 minus that is a big constant near 1. Okay, so in our example setting, which we think of, d equals 0.1 n, then we can take delta being, or 1 minus tiny. And by 0.1, maybe you make it 0.01, and then this tiny becomes even tinier. Okay, good. So then it's we can take delta, anything to be smaller than or equal to 1 minus tiny. So basically, it allows delta going very close to 1. Okay, so that's what the statement is up there. What exactly does this distance aspect mean? It means that the statement that delta of this at most say 0.99 means that there is an element of the Reed-Solomon code which differs from f0 plus z f1 in only 0.01 fraction oh, sorry, in 0.99 fraction of the coordinates. So the agreement may be only 0.01 fraction of the coordinates. Okay, so let me go over the statement a bit. I can go over the statement again, or yeah. Anyone? If there's a question, now's a good time to say something. Okay. So I'm now going to talk more about the statement. Let's take an example. Let's take a function which is a polynomial. It's perfectly a polynomial. We take f0 to be a function that's perfectly a polynomial, and f1 is a function that's perfectly a polynomial, but it differs in one spot. Okay, so f1 is almost a polynomial of degree d, and f0 is perfectly a polynomial of degree d. Then, yeah. So then, what's the so just as an exercise, what is oh, that should have been delta. What are these two expressions? The distance of f0 from Reed-Solomon codes. The distance of f0 from Reed-Solomon codes is 0. The distance of f1 from Reed-Solomon codes is 1 over n. Maybe the zero function as an example. Yeah, good. Okay, so right. So the distance between f0 from Reed-Solomon codes. This is a measure of how much like a polynomial f0 is. Okay, it is how many coordinates. What fraction of coordinates? So it's what fraction of coordinates of f0 to change. Of f0 to change to make it an element of the Reed-Solomon code. That's the quantity we're studying. If f0 is perfectly a polynomial, the answer is 0. This distance of f0 from Reed-Solomon is 0. If it differs from the Reed-Solomon, if it differs from a polynomial in just one coordinate, then the distance is then this delta of f0 Reed-Solomon, which I say in words, I call it the distance of f0 from Reed-Solomon, is 1 over n, because you have to change 1/n of the coordinates. Just one coordinate, changing that makes it a polynomial. Okay, so if you now take f0 being perfectly a polynomial and f1 being something that differs from a polynomial in one coordinate, then a random linear combination f0 plus z f1, how many coordinates will it differ from polynomials in? Okay, so I'm going to draw this setup again. Here's f0. This is the evaluation table of it. That's the set S. Here's f1. That's the evaluation table of it. What we're doing is we're taking this vector plus z times this vector, and we're writing down the value here. So that becomes f0 plus z f1. Z is a random element of the field fq. Then this is this plus z times this, and so on. What does it mean that something differs from a polynomial? I guess it differs from a polynomial in Reed-Solomon. Oh, good. Okay, that's a good question. So it means that, okay, so you had this polynomial, maybe x squared, right? So, and here are the, let's say S, the elements of S are alpha 1, alpha 2, blah, 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 till alpha n. Then, and we started writing the polynomial x squared. So then that's alpha 1 square is written here, alpha 2 square is written here, alpha n square is written here. That's how the true polynomial x square looks like. That's the vector that the true polynomial x square looks like. And good. Now, if you go to one of these entries and you change it and you write 10, there's some random value, then that's something that differs from a polynomial in one coordinate. How many coordinates do you need to change before the thing becomes a polynomial of degree at most d? So that differs from a polynomial in the Reed-Solomon codes. Exactly. Yes. When I say polynomial, I'm referring to polynomials of degree at most d. Yes, that's what. Okay, there's another question there. If d 0.1n, the d over n is 0, root d is which is not so tiny. What am I missing? Okay, good. Yes, your calculation is accurate, tiny, subjective. Perfect. Okay, so that was the answer. Right. So then if, yeah, so D equal to tiny times n, then square root of that is square root of tiny times n. Then we're looking at 1 minus square root of tiny, which is, okay, it's not so tiny, but it's subjectively very tiny. Okay. Good. Okay, so now I'm going to...
Wait, there was another question, I think.
Another question. What is for many z and few? Good. So that's a good question. So this for many z is something that depending on what you call many, the kinds of theorems that you can expect in this statement change drastically. This actually threw us off for a long time. So Ellie Shwangi and I have previous papers, and we also have a previous paper with Leo Goldberg, where we studied this question in different forms. And even in a previous paper, we even got an optimal result that you cannot improve with the square root being replaced by a cube root. And that was because we had a different word notion of many. So in this theorem, the notion of many is at least n square. Many is at least n square. And okay, so this is interesting only if q is bigger than n square. If q is smaller than n square, you can't have many z where this happens. So only in settings where the field is huge, well, square of the size of the domain you're evaluating. This is something that that is interesting. And so, okay, so that's the yeah, so okay, so and this theorem is false when you make z being n. If you when you make many mean for n values of fq. So this notion of many is something that has an impact on the kinds of statements that you can make. Good. So if you want to apply this to a real Frey setting, it better be that the field which you're working with is at least the square of the size of the domain where you're evaluating things. But from my understanding anyway, in Frey applications in real life, the field is big for other reasons. So yeah, at least
there's also a question in the chat. I'm not sure if you answered it already. Maybe I...
yeah, I think I answered that.
Okay, sorry.
Yeah, about differing, yeah. Okay. Good. So now, so we did a little toy example where f0 is perfectly a polynomial. Let's say it's the zero polynomial. It's zero everywhere. f1 is the x square polynomial, except it differs in one location from the x square polynomial, and I put this random value 10 in there. And when you take a random linear combination of these two, what will you get? Well, you'll get here z alpha. Oh, right. f0 plus zf1. f0 is 0. So it just looks like zf1. Does zf1 differ from polynomials of degree? How many coordinates of zf1 do you need to change before it becomes a polynomial of degree at most d? D is something bigger than 2. Well, it's sort of clear. You only just need to... So down here, you would have written z alpha 1 square, z times 10, z times alpha 3 square, and so on up to z times alpha n square. So yeah, you just have to change this one entry, and you're back to polynomial. Okay, let me do another example. The other example is, okay, so here is f0. It's a true polynomial of degree at most d for many coordinates, but over here it's junk. Okay, I just put in random values. Here's f1. It's a true polynomial of degree at most d, and here I put in some junk. Now let me take f0 plus zf1. how far will it be from polynomials of degree d? This is some 0.01 fraction of the coordinates. This is some 0.01 fraction of the coordinates. What will f0 plus z f1 look like? Okay, so I'm going to answer it. It will look like, well, in this 0.01 n fraction, 0.01 fraction of the coordinates, it will look like junk. In this 0.01 n fraction of the coordinates, it will look like junk. And here, it will look exactly like a polynomial of degree at most d. So the distance of f0 plus z f1 from polynomial, from the Reed-Solomon code, which is polynomials of degree at most d, will be about 0.02 for random z. For specific z, it might turn out that the random linear combination magically creates some agreements. But okay, but let's not. But that is going to happen for a very small number of z. But for most z, the distance will end up being 0.02. I'm sorry, 0.98. Here, the distance of f0 from Reed-Solomon is 0.99. Here, the distance of f1 from Reed-Solomon is 0.99. And a random linear combination had distance 0.98. This, okay, so this is not a contradiction to the theorem or anything. 0.98 is smaller than 0.99. For a random linear combination, the agreement is 0.98. And in fact, it is true that f0 and f1 are both close to Reed-Solomon. Okay, good. So this is another example that to keep in mind. Okay, so I'm now going to give some hint as to how you study such questions. The question is, yeah, so we want to deduce out of these many different f0 plus z f1s, they're all close to polynomials. For many different values of z, there is some polynomial pz, which is close to f0 plus z f1. Okay, so let me note that fact down. So for many z, we have a polynomial, and we mean we know it exists. And since this is just part of the proof, we can assume we can talk about it and use it. We have a polynomial pz of degree at most d prime, since that was the Reed-Solomon code we were working with, such that the distance of f0 plus z f1 from pz is at most delta. Want to find two polynomials, I guess q0, q1, such that the distance of f0 from q0 and the distance of f1 from q1 is at most delta. Okay. Yeah, so like I mentioned, there was some. We had two previous papers which studied this question, and they had different approaches to it. But somehow they were, they gave weaker bounds, and it was because they were more generic. They worked for more general error correcting codes than Reed-Solomon codes. But now we're using the fact that these codes are Reed-Solomon codes, and the And the key insight that that allows us to work here is to use decoding algorithms for Reed-Solomon codes. The decoding algorithm, the statement that I made above, the theorem about distances of functions from Reed-Solomon codes and random linear combinations, that's not an algorithmic statement at all. It's not saying there is an efficient algorithm given something to do something. It's just a combinatorial statement. But in the analysis of this combinatorial statement, we will take one of the well-known decoding algorithms for Reed-Solomon codes. So two of them. There's the Berlekamp-Welch decoding algorithm and also the Guruswamy-Sudhan decoding algorithm. These are really, really nice and elegant algorithms. I'll talk a bit about them now. We will take these algorithms and we will run them in our head on F0, F1, and F0 plus Z F1. And we'll see what happens when we run this decoding algorithm. And if F0 plus Z F1 or F0 or F1 was truly close to a polynomial of degree D, this decoding algorithm should succeed in finding the nearby polynomial. So the algorithm is used as a way to understand when a given function is close to polynomial, to a low degree polynomial. That's what the main insight of our result is. So let me mention two problems. So there's the decoding problem. This is an algorithmic problem. I give you a vector f, which is a function from the set S to the from the set S to the field FQ, and I want to know. All right, I want to find the nearest polynomial. That's one question. That's the decoding problem. There's a weaker problem called the testing problem, which is I give you a function f and I ask you, is it close to polynomials of degree D? Is it within, how many coordinates do you need to flip in order to make it a polynomial of degree D? What is its distance from Reed-Solomon code? And that's okay. So that's another question. Basically, the only way we know how to answer that second question is to answer the first question, to decode it. Decode it to the nearest polynomial, and then find, and then from that you know how many coordinates you need to flip. So the main question is, or rather, our only leverage into this weird notion, how many coordinates of a function you need to flip in order to make it a low degree polynomial, is the decoding algorithms that already exist. So we will use these decoding algorithms on these functions f0 plus z f1 and somehow try to understand the execution of the decoding algorithm and show that execution on a random f0 plus z f1 will also do something to f0 and f1, which is nice. Okay, so that being said, I'm now going to start slightly afresh and describe a decoding algorithm for Reed-Solomon codes. Okay, so this is already a really neat self-contained object. Given a function f, how do you find the nearby polynomial? Okay, so I'm going to talk about that now. Questions now, or comments or opinions about what I should say, what I should talk about? Is there anything to clarify? And along the way, I'll also give some opinion. I'll give a bit of insight into the proof. Okay, great. Okay, so I got one vote for carrying on, and okay, everybody else too bad. Okay. So this is the decoding problem. Given f from S to FQ, find polynomial P of degree at most D such that the distance of f from P is at most delta. This is roughly what the question is. This is what the decoding question is. Depending on what delta is, you can get different kinds of questions here. Okay. It's a really natural problem, let me say. It is noisy interpolation of polynomials. Interpolation of polynomials is, I give you some values, find a polynomial that fits through them. Usually the number of the degree of the polynomial that you will fit is the number of points that you gave me. Right? To fit through a curve through 200 points, you'll take a degree of 199 curve. Now if I ask you, okay, I give you 200 points, you're allowed to omit some outliers, find a polynomial that fits through 90% of the points. That's a whole different problem. It's extremely combinatorially, it looks very tricky, right? Because which subset of points do you omit? I mean, there can be lots and lots of subsets of points to omit. Yeah, so it's amazing that this problem can be solved in any setting at all. Good. So there are two really nice algorithms which are very natural for this problem, which are relevant to our work. So one is the Berlekamp-Welch algorithm. And a generalization of it, well, it wasn't a generalization of it called the Guruswami-Sudan algorithm. They're both absolutely amazing. I highly recommend, if there's anything you go and look at after this, just look at these algorithms. They're really, really mind-blowingly elegant, and it's a beautiful use of algebra, and it's all elementary. Each of these algorithms fits within a page of description and 1 page for analysis. Yeah. Okay. And at a very high level, the algorithm is based on the following. You're given this, so this is the domain S. We're evaluating, we have given some function f, and we're trying to find a curve that fits through it. So the idea is, we're trying to find a curve of the form y equals f of x, or y equals p of x, that fits through many of them, right? So we're ready to get something that like this, that fits through many of them. So the idea is, first find a curve that fits through all of them. Find a curve of possibly higher degree that fits through all of them, but not just a curve of the form y equals p of x. Find a more complicated curve. So you find a of x times y equals b of x. You find a curve of that form that fits through all of them. That's one kind of curve you could try to fit, or you could try to fit more complicated curves, some q of xy equals 0. That will look like, maybe, I don't know, there's a circle and a line. It could look more complicated. So the algorithm is based on finding a more complicated algebraic curve that fits through all the points, and from that, studying that, and then from that finding what y equals p of x could pass through many of them. That's what the main idea underlying these is. Okay, so these are what the algorithms are. I'm now going to draw a picture that captures the problem, that this f0 plus zf1 problem. So we have f0. So I'm going to draw the graph of f0. It looks like this. I'm going to draw and this is the z-axis. Then I want to draw a graph of f1, maybe, which looks like this. Okay, and now I'm going to draw some lines. And then I'm going to look at sections of this. So what I'm drawing is a surface. Yeah, I don't know if this is even accurate, but it looks like something. We're looking at this three-dimensional picture. What's the three-dimensional picture? It's we were looking at f0 plus z f1. Remember, they're both f0 and z f1 are both functions from s to fq. So there's actually a three-dimensional picture here, which is say g of x comma z, which is f0 of x plus z f1 of x. That's the graph of a two-dimensional function. If you fix any z, if you fix z, how does it look? That's this green curve over here. You fix z to be some value, it's something, it's this function of x, that it's this function of x. And what we know is that for many fixings of this z, this looks like a polynomial. Okay, so many green curves are delta close to degree d. So that's one statement. That's one aspect of the assumption. The other aspect of the assumption, so now if you fix x and don't fix z, then what kind of function is this? This is a linear function in z. So that these are the red curves that I drew here. Those are straight lines. Those are straight line functions of z. Okay, so all red lines, I mean, they are red lines, and their lines are lines, degree 1. So this is some kind of surface drawn in 3 dimensions. It's a 2-dimensional surface drawn in 3 dimensions, and it has this this property that sections along one direction are exactly straight lines, and sections in the other direction contain many things. So they don't contain degree d curves exactly, but they contain things that are close to degree d curves. Okay. And okay, so I don't know how I'm doing with time. I'll say in buzzwords and slogans how the proof of this goes. You take the you take one of these decoding algorithms, the Berle-Campbell or the Guruswami-Sudan decoding algorithm. So you take this decoder and run it on f0 plus zf1. We want to run it on the input f0 plus zf1 for many different z's. Okay. Yeah. So this is a function. This is decoding it for the code, the Reed-Solomon code of fq over the evaluation set s prime with degree d and d prime. Okay, I changed that. Okay, I'm calling it s. You know what I mean. Good. The decoder. Instead of doing this, to analyze all the decoding simultaneously, right? We're running this for many different z's, and in each case you have a decoder running. To do that simultaneously, there's just one trick that we do. We take the small z. Previously, small z was an element of fq. We replace it with capital Z, which is just a formal variable. So we now have a new received word, which is not f0 plus little z f1. It's f0 plus capital Z f1. This is a weird object. It's a function of, it's a it's a function not in the standard field FQ, but it's in a function in the field of rational functions over FQ. So that's what I changed here. Note I changed that and that. So we work not with the finite field FQ, but with the field of rational functions on FQ. So this is the field. So it's like the ring of polynomials in the variable Z, except you also allow quotients of polynomials so that it's a field and so that things are nice. Okay, so we run to analyze the performance of the decoder on many different instantiations of this little z. We replace that little z with capital Z and work with a big field. With this big field, we run the decoder over this big field. It turns out that when you run this decoder on the big field with the capital Z, that tells you a lot about how the decoder will work for every fixing of that big Z to a little z. Okay, so the main idea is run the decoder on this. What is this? This is a really weird object, right? F0 plus Z F1, capital Z F1 is a map from the set S to, what does it give you at every point? It gives you, when you plug in any little x into that, it gives you something, it gives you F0. So it maps, it gives you a linear function in Z. So it's actually a map, FQ. I'll write it like this, but actually, so F0 plus Z F1, that Z is capital now, the note, yeah, F0 plus Z F1 of X, that function at X is F0 of X plus Z F1 of X. So this is something of the form, so it's in FQ plus Z times FQ. Okay, so it's some linear function in Z. That's what the output value is. And this weird received word is what we run through this decoding algorithm. This decoding algorithm does all its algebraic mumbo jumbo. But what it does has the property that when you substitute capital Z equal to little z, it gives you what the, when you substitute capital Z equal to little z, you get what the decoder would have done had you fed in F0 plus little z F1. So this act of substituting capital Z equal to little z could have been done either before or after. And instead of doing it before, we'll do it after. Good. Okay, and since we have run the decoder, so that's the main idea. Once you have decided that this is the idea, the rest is lots of hard work. Yeah, so I'll mention two related papers that contributed heavily to our understanding. So one is Arora Sudan, which studies low-degree testing, and the other is the Hilbert irreducibility theorem, which went a lot into the Arora Sudan paper, but is also related to, and ideas around that are related to what we do too. So Hilbert irreducibility theorem, which tells you that if you have a multivariate polynomial and you say a many-variate polynomial and you restrict it to a random plane, then that restriction is still if you have a many-variate polynomial and it's irreducible and you restrict it to a random plane, then that restriction is still irreducible. And yeah, so ideas around both of these show up inside this analysis. But the main idea is to run the decoding algorithm on this formal received word F0 plus Z F1, where Z is a formal variable. It's not substituted. And then see what happens. Okay, good. So there's a question. What are the implications of this new result to fry or defry? Oh, great. So this change improves the soundness requirement for fry to 1 minus square root of the rate. So this now shows that a function which is far from Reed-Solomon, the Fry protocol, the original Fry protocol as described in BBHR, rejects it with probability exactly equal to the distance from Reed-Solomon codes, provided that distance is at most 1 minus square root of the rate. Previously, it was known that it was 1 minus cube root of the rate, and Deep Fry showed that it was 1 minus square root of the rate, but with some extra rounds in the protocol, which, okay, maybe you pay for it elsewhere. But now it shows that Fry is as good as that. So that's what the implication is for Fry. Good. Any other questions? So I basically said everything I had to say. Now I think is a good time for questions of all kinds.
Yeah, while we're waiting for final questions, I mean, also I want to thank Swastik. I heard this a couple of times from different places, but I personally enjoyed hearing it again, and from him it's always very lucid in my mind. And I see questions are collecting. I just want to point out that regarding things like Fry and Stark soundness, so what has been improved here is the proven lower bound on soundness. So, I mean, we actually conjecture in the paper and also in previous papers, similar conjectures appeared that the soundness is even better than what is proved here. And so far, we haven't seen any counterexamples or any refutations of that. We know that, but still, we want to. So higher soundness is better. But we also strive to push the lower bounds on soundness as far up as possible. This is push them further up to as far as 1 minus the square root of the rate. We know that they can't go beyond 1 minus rate. That's actually the upper, it's very easy to show that you can't go beyond that. The conjecture actually says that it's closer to that range, and that remains a terrific open problem for both Fry and Deep Fry. Sorry for...
Right, so actually the question was about that. Can you comment on conjecture 7.3 in the paper? So I think that is the conjecture which claims that, that you should be able to push this all the way up to the rate, 1 minus the rate. And also for fields which are of size linear in the size of, in n, O of n, we know that the field size cannot be little o of n or exactly n, but O of n possibly. Yes. So a lot of the results about Fry are closely related to this much more well-studied question of the list decoding of Reed-Solomon codes, and that's been heavily studied. And all the interesting examples and counterexamples in that setting are extremely algebraic. And anything remotely pseudo-random or anything like that, we have. I mean, usually we know you cannot get examples of such kinds. So, right. So basically, it's some general principle that, I mean, unless there's an obvious reason why it shouldn't be true, it should be true, and maybe just to work very hard to get it. And so I believe. I mean, I believe that conjecture. Still, as I stand, the procedure is extremely complicated. Oh, yeah, that's true. Is it possible that a proof bug could have slipped through the cracks? Is it likely given the complexity of the proof? Good one. So there's the exact quantitative behavior, and there's the high-level qualitative behavior. Is it possible that a proof could have slipped through the cracks? A bug could have slipped through the cracks? Okay, so yes, but only in the tiny quantitative optimizations. For qualitative, I would be extremely shocked and embarrassed. But there's a very clean, high-level outline. It has an there's an easier instantiation with this Berlekamp-Welch algorithm. There's a more complicated instantiation with the Guruswamy-Sudan algorithm. And before we wrote this version of the paper, we had a medium complicated instantiation with the Sudan algorithm, which is midway between. And there are very clear conceptual steps there. In order to make constants good and exponents of things good, we wrote it in as slick a way as clean and optimized a way as possible. So I don't think at the high level qualitative result there's any issue, and even say the exponents, no, but maybe constants. It's possible. I at the moment I strongly believe not, but I mean it's I understand this question. Good. from the perspective of an attacker trying to break Fry and break taxonomies, is there a constructive algorithm to follow? That's a good question. So we do know specific examples. So this comes from our previous paper with Leo Goldberg. We do know specific examples where the Fry protocol is not as sound as, but it's in an extremely structured situation. It's not as sound as the conjecture 7.3 asks would like it to be. And but that's excluded by conjecture 7.3. And that's in an extremely specific situation where the size of the evaluation domain N is the same as the size of the field FQ. And it uses some very, very specific algebra. For a Stark where so much else is going on, it's going to be impossible to embed this into that. I think if there's any place to look for attacking Fries and Starks, we know already from the deep Fry results that it's intimately connected to this problem of list decoding Reed-Solomon codes. So I think that would be the cleanest place to start. I mean, that's a very solid and concrete problem, which is very clean, and you can, that's very clean, and that's where there's something interesting, if at all. I don't believe that there is anything. I mean, this has been my favorite problem for 15 years.
I want to add to this. I mean, I think, so Justin is there's a very constructive, so first of all, I think it would be much easier to start by trying to attack Fry, because Fry, like Stark adds to it, more complexity, because there's some constraint system lurking behind in some statement. So Fry is very clean in the sense that it's, almost like an FFT, and it's all about linear algebra. So definitely trying to attack Fry is really good. I think so Swastik was referring to the fact that for deep Fry we even have a sort of a very proven connection to this very famous problem of list decoding. But what Swastik is saying, that even informally, it seemed that attacks would even for Fry, even though there's no formal reduction to list decoding, it probably, like a good starting point would be, so remember F0 and F1. Well, if I were to try and attack Fry, what I would do is I would start with F0 being this centroid of a ball of relatively small Hamming radius that contains many low degree polynomials that are somewhat in agreement with it, and then maybe make F1 that thing, and then try to somehow hope that there's such a multitude of seemingly low degree polynomials that if you add them up randomly, something good would happen. So I think informally, a good starting point, if you want to try and break Fry, a good starting point is to think about counterexamples for list decoding. So finding a function such that within a small radius around it, there are many low degree polynomials, even though that centroid will not be a low degree polynomial. And to add to that, the actual counterexample that Swastik was referring to is exactly coming from such a centroid in a very simple case where we know, so list decoding seems the most reasonable starting point for attacking Fry and deep Fry.
Yep. There's another. Is it like the proof can be simplified significantly when mentioned by non-expert? With the exact quantitative optimization, I doubt, at least the current proof, unless this, with interesting qualitative, instantiations of it that get the same qualitative behavior by a non-expert. Well, okay, no, non-expert is tricky. How much non-expert is the question? So by an undergrad math major, yes, then yes, I can. Yes, I think that is quite likely with some qualitative losses. non-expert like me, maths undergrad. Oh, great. Oh, yes. I mean, I don't. Yeah, maybe none of us are really experts. We're just. Yeah. Right. Yeah. I think then definitely yes.
I want to go on the record saying so. Swastik and I had many discussions of this nature, where I think we jokingly agreed that there's no algebra but linear algebra, and I mean all our results are such. If you unwrap them, it's basically it's counting dimensions of this or that. And the second thing is that ultimately, probably all results in algebra, they at the end of time, in the sort of the book of proofs by God, each one of them is like 3 lines. But no, it's so maybe it will fit one day in a few pages, but there's still a ways to go.
Right.
So I think that maybe on this happy note, we can. I want to thank on behalf of everyone. I want to thank Professor Swastik Gopalti. He's also an advisor to Starkware and a dear friend for many years. And thanks. So future Stark at Home episodes will likely feature other famous mathematicians and folks who contributed to research on proofs and things like that. So thank you, Swastik, and thanks everyone for joining me again.
Oh, great. Thanks, everyone.
Bye.